So now here's another example I want you to try on your own, and then put it on pause while you work on it, and then we'll go through the answer. Okay, so one of the things I want you to notice is we're talking about the surface that's formed by these concentric spheres. So I'm talking about this yellow, the yellow region is what's being enclosed by the surface. So the surfaces itself consist of both the outside and the inner part. So I'm going to call it S1 and S2, where we call the overall surface S. And so it's going to, rather than doing two different surface integrals over the outer sphere and the inner sphere, it's going to be a lot easier to use divergence theorem. So notice here when we find the divergence that we get 15x squared plus 15y squared plus 15z squared, and we're integrating over this region in between these two spheres. So it's really screaming for us to do a coordinate change and switch to spherical coordinates. And when we do that, you're going to notice that my row, my bounds, when I shoot an arrow radially outward from the origin, it enters the region when rho is 1 and it exits when rho is 2. And then phi needs to go its whole range, 0 to pi, and theta goes all the way around as well. So what I've sketched here is just a little cross section looking at it, but that's why you can see the inside here. This is like a little slice if you wanted to look, say, in the ZR plane, and then you rotate that all the way around so that your region is really this 3D shape. Okay, and then when you switch to spherical, you're able to detriple the integral, and we get 372 pi for the net outward flux through this region. So this is a good example of how divergence theorem is really going to combine everything, a lot of the things we've learned so far, because I'm trying to figure out the flux, but we end up doing it by doing a triple integral, and that requires a coordinate change. So we're really putting together all of our different skills we've learned so far in this application. Okay, and now let's try another one. So now I have, and I keep calling it D in these, I'd like to be consistent, let's call it E. E is the 3D solid region that's bounded between this paraboloid and this plane. So I'm just gonna do a tiny little sketch here. Here's the paraboloid, it's shifted down here, because it's starting at -4, so the paraboloid's going up like this. And then the plane here is at -3. Here's the plane. And so we're looking for the outward flux through this, just this part of the bowl. And so one option is I could do a surface integral over that bowl. But if you're noticing, my integrand already looks really crazy. And so it's likely I'm going to get a super, super messy surface integral. And right now, I can't use divergence theorem as it is because this is not a closed region. I could close it though, if I want, and that's going to be the trick here. The trick is going to be, let's close it off by adding a lid, and then we'll find the total flux through the whole closed region, and then we'll go back and subtract off the flux that was coming from the lid. And this is often a way that's helpful if you have a surface integral that's super messy. So go ahead, put it on pause, try that, see if you can use divergence theorem to do this, and then we'll check. Okay, so can't use divergence theorem because this region isn't closed, but we can make it closed. So S1 is the region where we're trying to find the flux, but we're going to also add S2. And then the total flux through S, which is the bowl and its lid, is applicable for using divergence theorem because it's a closed region and my partial derivatives of my vector field are continuous inside that region. And now let's notice, oh, and then this is just telling us what our plan is afterwards. Our plan afterwards is once we find the total flux through the bowl and its lid, we will subtract off the flux through the lid, and that will lead us the flux, or leave us with the flux through the bowl. So notice our divergence is pretty simple, x squared plus y squared. And it's then really suggesting that we do a coordinate change because I'm integrating over a region whose shadow, if I project it onto the XY plane, is going to be a circle. So we're switching to cylindrical here. And so here's my integrand in cylindrical is r squared, my Jacobian is r, and then let's check my bounds. To get my bounds, I'm shooting an arrow, I'm starting with z here, shooting an arrow parallel to the z-axis. It's entering along the bowl, which is r squared minus 4. Z is r squared minus 4. It's exiting along the plane, which is z is -3. And then the shadow, if you notice, the shadow is coming from the intersection of these two, the intersection of the bowl with the plane, and that's going to have a radius of 1. So in polar, when I go think about this shadow here, I'm going to shoot my arrow radially outward. It enters when r is 0, it exits when r is 1, and it goes from 0 to 2 pi. And then I'm going to just go from here with this integral, and I'll get pi over 6. Okay, next step is to do this surface integral over the lid, which is going to turn out to be much easier than the surface integral over the bowl. And the reason being, the lid, notice the normal vector for the lid. The normal vector for the lid is just k hat. And so when I take the dot product with f and n, I'm getting just the k component, which is z plus 7. And also you'll notice, and you could do this out the long way, but in this problem, ds will be dA because the surface I'm integrating over is exactly parallel to the xy plane. So when I project this pink surface onto the xy plane, I have not changed the area at all of that surface. So I just jumped in my head noticing that ds will be dA. You can do it the long way. You can find g and you can find p hat, and then you can actually do all the stuff with the surface integral. Like we've shown, you're still going to end up with 4. Here, let's just call that 4 dA, where we're now integrating over the circle. And this is the circle of radius 1, and we just need the area. That's really what that's asking. So we can see that that's just going to be area of a circle pi r squared. So just pi in this case, because it's radius 1, and then I multiply by the 4. Now you're probably saying, wait, where did that 4 come from? She jumped over that. So z plus 7 is my integrand, but I'm integrating along the plane where z is -3. So if you recall, when we do surface integrals, I need to get everything in terms of the plane where I've projected, which is going to be the xy plane. So I use information about the surface, in this case, that z is -3, to replace z. Sometimes you'll replace it in terms of x and y, but in this case, since it's just a plane, you just get to replace it with -3, which is going to lead me to just the surface integral of 4. So, okay, that's the flux that's coming through the lid. And then to get the total flux through, through the total flux through S1, which is what we wanted all along, which is the yellow bowl, I'm going to take pi over 6 minus 4 pi. So this is an example of a nice trick we can use if we don't have a closed region, is we can close it off and then subtract off whatever we added on.